there is this problem wherein we have this kind of a ceiling in which suspended from 2 points like this, A and B. Oh, sorry, it's not that way. The points are right on the ceiling, and we have a bead kind of thing. Okay, so the distance between these 2 points is, so this bead is labeled as C. And the distance between the points AB is L. So that distance AB is L, and there is a thread of length 2L attached between those points, and C is a bead which is initially, so C is slipping freely on the rope or on the thread. And it is released from that point, released from very near to A initially. So the question is asking that if the rope or the thread tightens, or it becomes taut at a certain instant. Okay, so let h be the height by which the bead falls when the string becomes taut, and v be the velocity of the bead just after the string becomes taut. Then we have to select some correct option. Okay. So basically what is happening is, as this is going down like this, some speed v as a function of the height through which it has gone down. So the initial state is that it started from rest just very close to the point A. So that bead started nearly at the point A. The bead would have started just from here, u equal to 0. At that point of time, the string is kind of lax like this. And at some instant later, we assume something like this is happening. Now, let's say the bead is somewhere here. But this is that limiting moment when the tension is still 0 in the string. Okay. Just before the thread becomes taut. Let's say this is that case. Okay. So this height is h, this is of course L between these two. And this point of time, this is having some velocity, let's say v1. Okay. And then an instant later, the thread becomes taut. Okay. So that the geometry looks almost the same, but that moment इसका velocity could change हो जाएगा. It becomes something like this. And the tension in the thread is not equal to 0. So between this and this moment, okay, that is when the crucial calculation will come. So of course, between this instant, so let us say this is state 1. Okay. That's the initial state. Then this is state 2, just before the thread becomes taut. And this is just after the thread is taut. So this is state 3. So between 1 to 2, states 1 to 2, what does that mean? You can just apply, one is that h square plus L square will become the hypotenuse. So the total length was 2L, remember. So this total length was 2L and this is L. So this length here, suppose that is x, that is nothing but 2L minus L minus h. So that's very easy, that calculation. You just apply Pythagoras theorem. And if this angle is theta, so you will get this as x square or h minus L. Oh, sorry, 2L minus h whole square. So you solve this and you will get the value of h as 3 by 4L. Correct. This you must have got. So this is one of the options. Okay. So now this half mv1 square is equal to mg h. So v1 you will get as square root of 3 by 2 gl when you put the value of h. That's 3 by 4L. So this is another option you will get. Now the important thing is between 2 and 3. Okay, so between 2 and 3, what is happening is there is a strong impulse. Okay. So between states 2 and 3. So one case is where the bead is having a downward velocity of that v1, which we just calculated. All this. So this is one instant. And then what happens is that on the wheel, there will be certain impulses which act. So those impulses will be like this. There will be an impulse J like this and an impulse of same magnitude J like this, but at this angle theta. Because remember the thread is frictionless, so it applies only a tensional kind of impulse. Okay. It should look like it's the same magnitude. It's more something like this. So this J is like a limit delta t tending to 0, p delta t kind of thing, where t is like a uh, impact impulse, impact point of time tension. So it is, that impulse picture is like this. As it comes, it will become like this. The tension will suddenly surge up initially, and then it will become constant after that, or it will reduce to a lower value. It will vary, it won't be constant. So that time between case 1 and case 2 is that delta t. And as a result of this, now you go into state 2. So between state 1 and state 2, this is what is happening. And then by the time you reach state 2, what happens is that so this angle is theta. You will see that the net impulse acts along the line, which is the bisector of this. So ये वाले line के along act करेगा net impulse. And coming back to the impulse diagram also, that you can see. So the net impulse is going to act along this line, which is bisecting this. So this theta by 2, this theta by 2. So along this line, the component of that momentum mv1 gets cancelled. So we are left with a final momentum, which is along this direction. Okay. So between this and this, you can see the net impulse is acting along this axis. If you take that as your y-axis and this is your x-axis. Understand? Very good. So this is theta by 2. Theta by 2. Okay. So ये y axis है, ये axis है. So the net impulse, which will be 2 times j cos theta by 2, is along y axis, the angular bisector. And this net impulse, it absorbs that component of momentum. So ये वाला component of momentum, that is mv1 cos theta. Whereas the x component of momentum, so to speak, this x component of momentum, that remains conserved. Because gravity is acting during that time, but that time is very small. So compared to the impulse due to the thread, the impulse due to gravity is neglected during that. So x component of momentum is conserved. So mv1 sin theta by 2. So v2 becomes v1 sin theta by 2. Now coming back to theta in the diagram, you will see that theta is tan inverse of L by h. It will further become tan inverse of 4 by 3. So it is nearly 53 degrees. So from this, your V2 will become square root of 2gh sine 53 by 2, or square root of 3 by 2 gh sine of 26.5 degrees. And this was one of the options given in the question, the MCQ question, and the other was the value of h itself. So this becomes the answer. Okay. So hope the question is clear to both of you guys. Okay, now I'll come to the other question also. Omkar, you also, hope the question is clear. So this was the original question, in case anybody has missed it. This is the question here. Right, so I'll just give you a moment for this, then we'll come to that heat and thermodynamics problem. Okay, so hope this is completely clear, guys. So as this initially falls, there is no tension in the thread till this thread is slack. So it's free fall. So from A till this reaches this point where the thread is about to become taut, just before it's become taut, it's a free fall हो रहा है. So your V is equal to root 2g. It's very simple. And H comes from geometry. That's all very simple. But now between this state and this state, when the thread is geometrically in the same situation, so this angle theta and this H are the same. But एक case में thread taut होने वाला है, and in the other case it has become taut. So during that time, there's a sharp impulse which acts through the linear direction of both the threads because there's no friction. And because of that, because it's one common massless thread, the magnitude of that impulse will be same. but two parts of the thread will apply along their respective directions. So that is the net impulse that the thread is applying between just before it has become taut and just after it has become taut. So that impulse, what it does is it acts along this net direction, which is the angular bisector. So it cancels the momentum in the opposite direction. So it was falling down V1. So it had this component of momentum, this Y component of momentum, and it had this X component of momentum. Now it's basically, you can think of it like this, that these two sections of the thread, they are acting like a resultant thread which is along the angular bisector. And the two impulses, you can replace them as if there's one single thread, which is along the angular bisector. So a single thread kaisa impulse laga? It would apply an impulse along this y-axis, which would cancel this negative y component of momentum, and the x component of momentum would be conserved. That's what's happening here. Okay, so it's just a slightly more complicated version of this kind of question, where you have a single thread and this thing attached. If you just have a single thread and you drop a particle from somewhere here, but the thread is not attached. If it comes into free fall, then somewhere the thread becomes taut. So wherever the thread becomes taut, वहाँ पे ये component of momentum conserve हो जाता है, whereas ये component of momentum impulse absorb कर लेता है. So here there is a single impulse acting, J delta T, which is doing that. Here there is a combination of two impulses acting, but they act like a resultant impulse along that angular bisector. Okay, so you can think of the problem simplified in that form. Right, now coming to that question related to that heat pump. So this was the question, that as if you have some kind of a building, the inside temperature is T, the outside temperature is some T naught, and it's radiating heat, so it's also losing heat. But there is a heat pump which supplies heat from the outside. Let's say it is absorbing heat at the rate of delta Q1 by delta T. It's supplying heat at the rate of delta Q2 by delta T, because it's absorbing a certain amount of power. And it's an ideal heat pump. This one is an ideal heat pump. And also the rate of heat loss, presumably because of radiation, that is equal to some alpha, some coefficient into T minus T. Okay. T and T naught are in kelvins. So this was the idea. Okay. Now remember, it said it's an ideal heat pump, so we should assume that it should have maximum possible efficiency. So maximum possible efficiency. So that is the efficiency of a reverse Carnot engine. That concept we use. Okay. So let's revisit Carnot engine. So Carnot engine takes heat from a heat source at temperature T1, dumps heat into a heat sink at temperature T2, and does a certain amount of work. So we have W by Q1 is equal to 1 minus T2 by T1. This is a Carnot engine. So you can see W is equal to 1 minus T2 by T1 times. And Q2 is equal to Q1 minus W. So a reverse Carnot engine, what will that be doing? Be doing this. Okay. So again, it's the same thing. So again, W by Q1 is equal to 1 minus Q2 by T2. Q1 will be equal to W into 1 minus Q2 by T1. So delta Q1 by delta T, this is the rate at which heat is supplied into the room, into the building, will be equal to delta W by delta T, which is the power consumed by into 1 minus T2 by T1 की जगह कितना हो जाएगा? T0 by T हो जाएगा, because now this is the building. So your T1 is equal to the temperature of the building, and this is the atmosphere outside. So T2 is equal to T0. Okay. So this is your relation of, you can say, delta Q by delta T supplied by the, that is equal to the power into 1 minus T0 by T. So now at equilibrium, at thermal equilibrium, क्या होना चाहिए? मेरा delta Q by delta T supply should be equal to delta Q by delta T radiation loss. Okay guys, so hope you are understanding this now. So this power into 1 minus T0 by T will become alpha into T minus. From this you should be able to get the equilibrium temperature. This is a quadratic relation. So now solve this for T in terms of T0 and other constants. So the key word there was that it's a ideal heat pump. So that's where we get the idea that it should have the maximum possible efficiency. So maximum possible efficiency means it's like a reverse Carnot Engine. You guys, hope you are all familiar with the concept of refrigeration cycle or reverse heat engine and how the efficiency of that works. So people, is this clear? I think this question had been pending for some time. Okay, very good. So this question had unfortunately been pending for some time. One of you had sent it to me earlier and I had sent some explanation but not the full solution. So, all right. So just take a quick note of this if you like. Now let's move on to the SHM question you had sent. So that is mainly about constraint relations and all that. Okay. So obviously I'll supply you the PDF so you can go through the details of the solution. If you understood this, it's fine. Now this one is a little bit lengthy, but so in this example we have cylinder like this. It's lying on a rough surface. Now there is a spring attached from one side to a wall kind of thing. And from the other side, we have the thread which is going around another pulley, right? It's going around another pulley. It's a combination of two pulleys. Just a moment. Like this thread which is going around a fixed kind of pulley like this, which is frictionless. This is attached to the ground, and then this thread is further going up. Going down another pulley, which is also a massless and frictionless pulley, but attached to another spring over here. That's attached to some ceiling. And then the thread coming out from this side is attached to yet another spring. We have one more spring in our system. Vertical like this. So anyway, so this is K, this is, oh, this doubt is solved. Okay, great. So you understood constraint related. So then let's move on to some more questions. Any other doubts pending, guys? Just send it to me in due course. I will. From what I have seen in the messages, I think only these doubts were remaining this week. So, all right. So let's move on to some more questions. So I wanted to solve some questions related to conservation of momentum as well as rotation combined. Those type of questions. We have a wedge of mass 3m, and this is a solid sphere of mass m, radius r. Now, this angle is 37 degrees, and this height is h. So you have to actually imagine in the figure that r is small compared to h. R is a few centimeters, and h is of the order of few meters. So it's negligible kind of thing. And this is a rough surface. So the sphere is released from the top of the inclined surface of the wedge at t equal to 0. So given that m1 is to m2 is equal to 1 is to 3, theta is equal to 37 degrees, h is equal to 20 meters, and g is equal to 10 meters per second square. this h is also given 20 meters. You have to find the speed of the wedge at the instant when the sphere is just about to hit the ground, just about to come in contact with the floor, and the time taken for the sphere to roll down the inclined surface. So in this question, you will assume that there is no slipping between the sphere and the inclined surface. This is a smooth surface. The floor is smooth, but assume no slipping between the wedge surface and the sphere. Okay, so just try this out, people. Okay, so we can continue working on the problem. I will just start with the free body diagram and all this. So the thing is that since the question is already asking for time, so what I will do is I will take the acceleration approach. Okay. So since we have to solve for time, calculate accelerations and use kinematics for finding speed and all that, because the acceleration will be uniform. There will be uniform accelerations. So that is the approach I'm going to take. You can of course take the work energy approach also, and I'll discuss that also. This is the reference frame of the wedge. So it's a non-inertial frame. So I'm assuming that the wedge is accelerating at some A, and this guy is accelerating relative to the wedge at some E relative, and angular acceleration is alpha. So my reference frame here is accelerating like this. So in this reference frame, the forces acting would be pseudo force. And pseudo force will act through the center of mass, weight, normal reaction, and rolling friction. These are the forces. And in this frame, this will be having a relative acceleration along this direction, and an angular acceleration in this direction. And the point of contact should have zero tangential acceleration. So this AR is the acceleration of center of mass with respect to wedge, mass of sphere with respect to the wedge. So that is what this relative acceleration is. So in the wedge's frame, the tangential acceleration of the point P should be 0. So E relative should be equal to R alpha. And MA cos theta plus mg sin theta minus friction should be equal to MA, and friction into R should be equal to I alpha. So solving these three equations, you will get this, that E relative will be equal to E cos theta plus G sin theta upon 1 plus I by mr square, and I you will take here as 2 by 5 mr square. So we get this relation. So let's see equation E. It's coming from 1, 2, and 3. Now for the wedge, you don't need to solve the FBD because we can apply the condition of center of mass of the system. Okay, so again, now to solve for this A finally, the more efficient way rather than solving the FBD of the wedge, because then we'll have to involve normal reaction and all that. तो सबकी जरूरत ही नहीं है. What we can just use is the concept of center of mass for the whole system. So let's see how that works out. So my wedge is moving in the ground frame with some acceleration E. And my sphere went somewhere. Back. Sorry guys, tech goof up. So this sphere is having an acceleration relative to this now, like this. And the whole system, as you can see, the external forces on the system are only the weight of this body, and the normal reaction from the ground. These are the only external forces on the system. So external forces are vertical for the system, which we consider as the wedge plus sphere. So we can say that horizontal momentum is equal to 0 and it is conserved. Initially it was 0. So system's x component of acceleration of center of mass. So the system's center of mass is x component of acceleration should be 0 for the system. So that means m2 into a2's x component plus m1 into a1's x component should be 0. Okay. So that vector relation, relative acceleration is like this, and the acceleration of that frame is like this, and this angle is theta. Okay, so this is m. So m into e relative cos theta minus e, that should be balanced by this. Okay. So m2 is equal to 3m. So 3ma. So this becomes my equation Bs, which is coming from consideration of center of mass is horizontal momentum being conserved. Okay. So now solving A and B becomes pretty simple. You can see equation A will actually give you 5 by 7 into 0.6g plus 0.8e, because theta is equal to 37 degrees. And equation B will give you that E relative into 0.8 cos theta is equal to 4e. Okay. So E relative is equal to 4 upon 0.8. So that is 5 by 2. So substitute that back here. So we will get this. Just check my calculation once, but this is what I'm getting. And E relative will work out to be 5 by 2 times E. So meters per second. So now I will use kinematics. So once I've got this, I will use kinematics. I don't need to do any other dynamical calculations. That's the advantage of using this method to find out acceleration status, rather than going for the work energy and conservation of momentum method to first find speed. But then what do you do about the time? Okay, people, so hope this is clear. Alright people, so hope this is clear, and you should be getting the same thing by solving. So now once we know this A relative and A, what we can do is, you can see that we come back to the motion of the sphere with respect to this inclined plane. So let's say we are standing on this inclined plane. So in our frame, the sphere is starting from here at t equal to 0 and reaches here at some time t with some speed vr. So during that time, it is going down with A relative. Okay? And we can calculate this length because we know this height. So we can see that half A relative into t square should be equal to h by sine theta. So this time taken will become square root of 2h upon A relative sine theta. So square root of 2 into 10, so 2 into 20 divided by A relative, which was 75 by 31, sine theta, which is 3 by 5. Okay. So this will give us the time in seconds. And once we got the time in seconds, we can also calculate the wedge's speed in the ground frame at that point of time. Let's say V. So V will be nothing but A into T. So that will be your 30 by 31. That goes our A, I think, into this time. This will be the speed in meters per second. Now I'll show you another approach we can take in this question, which is the work energy approach. But still we will have to calibrate the acceleration eventually. So we will see how to make use of that. Okay, so people hope these calculations are clear. Okay, so now let us take a different approach to this, which is the work energy approach. So let us say at some point of time, a system has reached some kind of state where the sphere is here. Now at this instant, let's say this is moving with the speed v, and relative to this inclined plane or relative to the wedge, this is having v relative and an omega like this. Okay. So relative to this is made a vertical displacement of y and a displacement in this direction. S. So we have for the system, horizontal momentum is conserved and equal to 0. So we have again V relative V theta. This is the sphere which is of mass m, and this is the wedge which is of mass 3m. Okay. So this is giving us that m into V relative cos theta minus V is equal to 3m into V. So again it is telling us that V relative cos 37 is equal to 4V, or V relative is equal to V into 5/2. That's equation 1. So at any point of time there is this kind of constraint relation between the linear velocity of the wedge and the relative linear velocity of the center of mass of the sphere with respect to the wedge. Then we have got conservation of mechanical energy of sphere plus wedge plus the Earth's gravitational field taken as a system. So again, if you look at the sphere, its velocity is the vector sum of this V and V. The sphere actually has, in the ground frame, the sphere's center of mass actually has some velocity which is like this, and some angular velocity like this. So first of all, V relative will be equal to R omega for no slipping. That's a constraint relation. And kinetic energy of the sphere in the ground frame will be half m VCM square plus half ICM into omega square, where VCM is the velocity of the sphere's center of mass with respect to ground. So VCM will be the vector sum of V plus V relative. So VCM will have a magnitude of square root of V square plus V relative square minus 2 times V relative cos theta from this vector relation. So kinetic energy of the sphere will become half m cos theta. Okay. Kinetic energy of the wedge will be equal to half 3m into V square. Okay. And change in potential energy will be minus mgy. So we can say that kinetic energy of the sphere plus kinetic energy of the wedge minus or plus change in potential energy of the system should be 0, because rolling friction does not do work. Okay. So is this plus half I omega square? Forget this. Okay. Where of course omega is equal to V relative divided by R, and I is equal to 2 by 5 mRs. So we can make use of all this equation now, that this is going to be half mv square So the translational kinetic energy of the sphere plus the rotational kinetic energy, we can write this as now 2 by 5, ये term हो जाएगा half into 2 by 5 into v by r whole square. So this will become half into 2 by 5 mv relative square. Okay, this plus half into 3m v square minus or is equal to mg by. Okay. Now we know that, so this is like our second equation, that we can simplify this a little. So write this as half into 1 plus 2 by 5, so that's how much, 7 by 5 v square plus, sorry, v relative square plus 1 plus 3, so that's 4 v square minus 1.6 v into v relative is equal to gy. Cancel the m's. Okay. Now we have this relation that this vertical displacement is y, this displacement is s, and along this direction this is dr. Okay. So we have this relation that v relative is equal to ds by dt, which is d by dt of y by sine theta. So it is 5 by 3 dy by dt. So v relative is equal to this, which is equal to, now v relative was how much in terms of v? From equation 1, it was 5 by 2v. Okay. So 5 by 2v is equal to v relative, which is equal to this. Or v is equal to 2 by 5 v relative is equal to 2 by 3 dy by dt. So we're going to make use of this like a constraint relation when required for acceleration. So one is you can solve this for v, okay, as a function of y. That is one thing. Okay. So that will give you the answer to the first part. And the other is you can solve for v relative as a function of y, then differentiate that. Okay. Then differentiate with respect to time. Okay. So that will give you E relative. Okay. And then use the relation that half E relative into T square should be equal to H by cos theta. So you will get the time when it reaches the bottom. So that is the second part's answer. Yeah, sorry guys, I just lost connection for a moment there. So, people, are you clear with this work energy application? Just if you can answer me, if you've have you reached up to this step? Have you reached up to this step here? Okay, good. Okay, so let us just solve this for the relative acceleration thing. Then we can be sure that our first solution is also correct. So now in this equation, what you do is you substitute this thing that v is equal to 2 by 5 v relative. This thing, that v is equal to 2 by 5 v relative. So substitute in this equation, v is equal to 2 by 5 v relative. So what will that give us? Let's see that next. Okay. So I'm just going to pick this equation out. It's too much to copy paste and all. Okay. So in this now I'll substitute v is equal to 2 by 5 v relative. So I'll get half of 7 by 5 plus 4 into 4 by 25, okay, minus 1.6 into 2 by 5. V relative square is equal to g by. Minus, this is right, that 16 by 10 or 8 by 5. So this will become 16 by 25. Yeah. So we'll get 7 by 10 v relative square is equal to gy. So differentiating this on both sides now. So differentiate, we will get 7 by 10 into 2 v relative into e relative is equal to g into dy by dt. And now use that other constraint relation that we have. This one. V relative is 5 by 3 dy by dt. So 7 by 5 into 5 by 3 dy by dt into E relative is equal to 10 into dy by dt. So E relative we will get as t by 7. Meters per second square. It's not the same as we had got earlier, so there was some mistake somewhere. Oh, there's a mistake here. It should have been 5 by 2. So there is mistake here. Yes. So these steps I'll have to redo. So this will give us 35 minus 8 by 14 is equal to this will give us E as 30 into 2 divided by 35 minus 8. Is 27. Something going wrong with the calculations. Just verify this whole thing once more. This also is not correct. What did I do wrong here? This was wrong. This is also wrong. So now let's put 5. So let's put that here. So 5a is equal to 5 by 7 into 6 plus 4 by 5. So 5a is equal to 30 by 7 plus 4 by 7a. So anybody got the calculation? So I am getting A as this. Therefore, I should get E relative as how much? 5 times this. I am getting something different here. Okay guys, I will go through the entire calculation of this. Let's not waste time on this here because I like to do some more questions. Has anybody done the calculation? No, no? Okay. So just complete this calculation later. I'll also complete it and send to you. But you understood both the methods? Okay, Omkar. And Chakshu and Bhaskar, have you understood the methods? The FPD and acceleration method as well as the work energy method and differentiation. Okay. So just complete the problem by both the methods later and verify that answer should come correct. By both the methods. Okay, now moving on. The next example I want to discuss is a very simple situation actually, but there is an important concept based on this that I want to discuss. So we have some kind of a smooth combination of inclines like this. Now this is a thin uniform rod. Now this is a 60-degree. Both the surfaces are smooth. So initially the rod was against the inclined surface. And released from rest. So now find VCM at an instant when theta is equal to 30 degrees and omega about the center of mass. So what will happen is by the time, so initially your rod was against the inclined plane like this and it started slipping. So this is the initial state. U is 0, initial angular speed is 0. So from this state, as it comes to this state somewhere here, by now the center of mass has some velocity, let's say like this, but not along the rod, not necessarily along the rod, that is. So the center of mass velocity is not necessarily along the could be in some general direction like this. Okay. And you can see that it will have also this kind of an angular velocity, omega, about the center of mass. So we have to find this VCM and this thing at a particular instant when there's this angle theta with the floor that changes from 60 degrees initially because it was against this to exactly 30 degrees. Okay. So hope the question is clear, guys. Okay. So this is a clean calculation question. It will not be so tricky in terms of lengthy in terms of calculation. You can just try it out. Through this question, I want to discuss one important concept with you about rotation. Okay, Chakshu, I'll help you out. Don't worry. So essay type of problem, one trick you can use is instantaneous axis of rotation. Okay, so let me just explain to you how that works. So you notice that what is happening in the problem is there is a constraint, and what is a constraint? That your rod has to move between the two surfaces. No? So that provides a constraint in the system. So rod को ऐसा move करना पड़ेगा कि रॉड का एक सेक्शन जो है या एक एंड जो है इस सरफेस पे मूव कर रहा है, that is providing you with one constraint, so called, okay? And the other one is moving on this surface, so that's providing you with another constraint. So the moment you have this kind of constraints for the two ends of a body or a rod or whatever, you can use the concept of instantaneous axis of rotation. Are you guys familiar with the concept of instantaneous axis of rotation? Okay, so let me explain how you will use that first here. Then we'll go back to the theory thing also and understand that in more detail. So this is the end of A of the rod. This is moving with a horizontal velocity V. If this is the end V of the rod, this is moving with a velocity along this surface, which is at an angle theta. Okay. So the trick that we'll use over here is that we will drop a perpendicular from this point. And we will drop a perpendicular from this velocity, and wherever they intersect, that will become my so-called instantaneous axis of rotation. So the rod's state of motion right now is in that it is in some kind of rotation with angular speed omega about that point. Okay. So the velocity of, so let's label that point as our origin actually, instead of our center. So the velocity of any general point P becomes omega cross of that position of that point P with respect to O, where O is the instantaneous axis of rotation. Okay. So in this diagram you can see that if this distance is RA and this distance is RB, then VA should be equal to RA into omega, VB should be equal to RB into omega, and more importantly, now the center of mass is sitting here. So let's say you drop a position vector onto the center of mass from that point. Okay, so this is R of center of mass with respect to instantaneous axis. So the velocity of the center of mass should become, let's say like this, in general, like this. Okay. VCM should be equal to R omega, RCM into omega. So this is one thing we'll make use of. And the kinetic energy of the body is half m VCM square plus half I omega square, where this I is moment of inertia about center of mass, and this omega is omega about instantaneous axis, is the same as the omega about center of mass. Okay, so that is the concept that we use over here. Okay, so we'll come back to the derivation of these equations and how this works and all that. But are you familiar with the absolute basic of this concept now? ये वाला concept आपको familiar है? Guys, if you can, okay. Chakshu and Bhaskar, is this concept clear to you? Okay, Bhaskar. Chakshu, what about you, beta? This is clear? Okay, good. So I'll come back to a more detailed description of this, but before that, so we have this relation now, okay, and we have this. So since there's no friction, we will make use of this relation for work energy, conservation of energy, okay, and we will use geometry to use this as a constraint relation. So now notice what is happening when particularly my theta is equal to 30 degrees, I'm getting a very symmetrical situation. Okay. Just give me a second, guys. My screen has hanged. Just a moment, I'll restart. Okay. So if you redraw that diagram, which I had done for a general theta with a particular case of theta equal to 30 degrees, you see you get a very, it's like a lucky thing. At that instant, that triangle is a very easy triangle to solve. And you have an easy solution of this whole thing. The relation between VCM and omega, उसका relationship बहुत easy हो जाता है. So you know this type of a problem is designed to be done by instantaneous axis of rotation method. So whenever you see a situation like this where you know you have this kind of a constraint, okay, that two of the points on the body or any two arbitrary points, in this case the end points of the rod, they are constrained to move in a certain way along a surface. You know that you can find the instantaneous axis very easily. So you should always try this method. In case it doesn't work, then you go back to the general method. But if it works, then it's a nice trick for solving the problem. So let's look at how that trick is working here for the particular case now where theta is 30 degrees. So the particular case where theta is 30, is happening in that case. Because this is 60, the instant when theta is equal to 30, this also becomes 30. Okay. And therefore, when you drop these two perpendiculars, the point where they intersect will be this kind of point where this will be forming a which type of triangle now? Equilateral triangle. You can see that in the diagram. This will be an equilateral triangle because क्या हो रहा है? इस point का velocity ऐसा है. So that means this angle has to be 60 degrees because this whole thing is 90. Okay. And similarly, this end of the rod, the velocity is in this direction. So this angle is 90. So this angle has to be 60. So this is becoming an equilateral triangle. So since this length is L, so this is also L. So that particular instant is a very easy triangle to solve. So when you drop the position vector of the center of mass from that point, it is just the bisector of the equilateral triangle. Okay. And interestingly, at this moment, the center of mass's velocity, इसका direction इसके along हो जाएगा. Only at that instant. In general, this will not be the case, but at that instant, VCM's direction will be along the rod because it's an equilateral triangle at that instant. So this r of center of mass with respect to instantaneous axis, it will have a magnitude of root 3 by 2l. So if the angular velocity of the system about the instantaneous axis is omega, so you can see that VA will have the same magnitude as BB, which will be equal to L omega, and VCM will have root 3 by 2 L omega. So this is the more important equation for us. So this is one thing. So the kinetic energy of the rod will become, this is rotating about the center of mass with the same omega as it is rotating about the instantaneous axis, A omega. So the kinetic energy of the system or of the rod become half mvcm square plus half I about center of mass into omega square. Okay. So that will become over here now. Square by 12 into omega is how much? 2 by root 3 VCM by L. Okay. So we can write this whole thing as half mvcm square into 1 plus ये कितना हो जाएगा 4, so 1 by 9. Okay, just check my calculation. This factor is 1 by 12 into 4 by 3. Yeah, so 1 by 9. Okay. So this will become 4 by 9 mvcm square. This kinetic energy. Now this kinetic energy is coming as a result of loss of potential energy. Okay, so your rod is going from an initial state where it was, let's say, like this, to now a state where it is like this. So its center of mass is going from a state where it was here to a state where it is here. 5 by 9, okay, I'll just check it. So this is where the center of mass was. Now this is where the center of mass is. Oh, sorry, yeah, correct. It's 1 plus, not 1 minus. So it's 10 by 9 into half. Okay, guys. Okay, so change in kinetic energy plus change in gravitational potential energy should be 0. So this half mvcm square plus half I omega square plus mg h1 minus h2 should be 0. Okay. So 5 by 9 mvcm square should be equal to mg h2 minus h1. So 5 by 9 VCM square should be G into कितना हो जाएगा L by 2 sin 60 degrees minus sin 30 degrees. So 5 by 9 VCM square should be GL by 4 into root 3 minus 1. So VCM come out to be 1 by 2 comes outside. Sorry, 3 by 2 comes outside. Square root of GL 3 minus 1 by 5. So this is the instantaneous axis of rotation way of solving it, and as you can see that if you gauge this in the beginning only, it's quite an easy thing. For that angle 30, it's quite easy. If you take some other angle like 45 and all that, it will become more complicated. But still, it's solvable. ऐसा नहीं है कि solvable नहीं है, but the whole triangle becomes a scalene triangle, so it's a bit more complicated to solve. Okay, so just note this down and just verify the calculation once. Then I'll also show you the general method. Okay, so are you guys getting this better? All of you are clear with this? Okay, good. Now we'll come back to instantaneous access method. Okay. But what is another way of understanding this? Another way of understanding this is basically the same thing. The constraint that the rod is moving such that those 2 points are moving on 2 surfaces. But those constraint को हम अलग तरीके से use कर सकते हैं. And how we can use that is something like this. $30. So let's just like this. Okay. Now, in this, if we assume that the center of mass has some kind of general velocity, okay, so this becomes a little tricky over here. But if it has some general velocity, we'll assume that it has 2 components of velocity. The next component like this, let's say, and a y component like this. And obviously, about the center of mass, there is some angular velocity omega like this. Okay. So this is the state of the center of mass. So if the center of mass has some velocity, which taking a normal system of axis is minus vxi cap minus vyj cap, and there is some angular velocity omega, which you can see is going into the plane. So I'll write it as minus omega k cap like this. Then the velocity of any general point, in the body will become what? It will be given by this relation. It is the velocity of that point with respect to center of mass plus velocity of center of mass. So it is omega cross of r of that point plus velocity of center of mass. So this is the general theory here. Instead of instantaneous axis, we are using this concept. Okay. This is velocity of a point P at the position Rp with respect to center of mass. So now let us apply that concept to the point E, which is this point here. So let's say this point E. Now this one's velocity we know is in this direction. So ये जो velocity VA है, it is actually the sum of what? These two things. So for that point E, you can see that point E, because of the rotation of the rod, it has a component of velocity in this direction, which is L by 2 omega, because of this omega. And because of the linear motion of the center of mass, it has Vx, and because of the vertical motion of the center of mass, it has Vy. So if this angle is theta, here you can see this angle is 90 minus theta. So the fact that the point E has VA along negative x-axis. So we have a constraint relation that L by 2 omega cos theta has to balance Vy. So in this case, we have root 3 by 4 L omega. So cos 30 will be root 3 by 2 is equal to Vy. And then similarly for the other point, we have the constraint that this point is moving along this axis. So for this, the constraint is a little bit more complicated. But luckily for us, again, because this angle is 30, it will be a little bit easier to solve. So this angle is 30 right now, so this angle is also 30. So this point B is having, because of the rotation, it's having a component of velocity like this, which is L by 2 omega. And because of the translation, it is having a component of velocity like this, and one more component of velocity. Vy and vx like this. Just make this a little bit congested. Vy is like this, and that L by 2 omega. Okay, so now what is happening? It's component of velocity, which is along this line, which is perpendicular to the surface. This has to become 0. Right? So here, this angle will be 60. And that angle will be 30. Because this angle is 30. So this is quite complicated. But anyhow, so you will have to make the component of velocity along this axis. This is, let's say, the normal axis. So component of velocity of v along the normal should be equal to 0. So that will give you the required constraint relation. So that point V, as you can see, with respect to this surface, is at 60 degrees and it's normal. So it's having what all velocities? Let's just work those out again. It is having Vx, Vy. So these are the easy ones. And also the rod is lying along this kind of a direction. The rod is lying along this kind of a direction. This is the direction in which the rod is lying. So escape perpendicular. So that L by 2 omega term is perpendicular to this. This is where life is a bit complicated for this one. So you realize that L by 2 omega is making an angle of 30 degrees because Vy is making an angle of 60 and this angle is 60. So this thing will now give us a constraint that Vx cos 30, that is the component of this guy along this direction, has to be balanced by the component of these two, that is Vy cos 60 plus L by 2 omega cos 30. So let's see what that is. So root 3 by 2 Vx is equal to Vy by 2 plus root 3 by 2 into L omega by 2. So this should give us root 3 times Vx is equal to Vy plus root 3 by 2 L omega. This is the next constraint that we where above we had our equation 1 was coming from the similar kind of constraint. Now we have this, and then we have the work energy. So that is same as that figure over there. Only thing is here we will replace bx square by square plus ml square by 12 omega square. Sin 30, same thing as cos. So you will have again this term. Now in this third equation, you will have to start incorporating these constraints. The easy way to do this is that from equation 1, you already got Vy in terms of omega. You got Vy is equal to 3 by 4 L omega. You got this. Now substitute that over here. Substitute from equation 1. Vy is equal to root 3 by 4 L omega. So you will get Bx as this. Root 3 Bx is root 3 by 4 L omega. That's your Vy. Plus root 3 by 2 L omega. So root 3 cancels out. So you get Bx as 1 by 4 plus 1 by 2. So that becomes how much? 3 by 4 L omega. Now you see you will get that constraint that we got earlier. So your Vcn, which is root of Vx square plus Vy square, will become L omega square root of P by 4 का whole square plus root 3 by 4 का whole square. L omega by 4 square root of 9 plus 3. 3 by 2. And this is what we had got by the instantaneous axis of rotation. So you can actually put this directly in the so you get the same. So this is the proper rigid body constraint method of movement without using any shortcut and all that. But you can see how this problem is actually designed to be done very fast by the instantaneous axis method. So just go through this once. अगर ये inclined surface के जगह wall होता, so this constraint method would have been much easier because A would have given you a relation between Vy and omega. B would have given you a relation between Vx and omega, and that's it, that's done. But because B is along the inclined plane, this becomes very complicated actually. So the IOR method, the instantaneous axis of rotation method, is very important for a problem like this. So I'll just leave you with a few seconds to go through this. Including the diagram and everything, because it's quite complicated. So this diagram over here, the DB one, this was a little bit extra complicated, so I made it again below. So this one in more detail is over here. So in this diagram, this angle is 90. This is that normal line. This is normal to the inclined plane. This is the inclined plane itself. The rod I have not drawn because it just adds complication. But from here you can understand why this L by 2 omega term, this L by 2 omega term is like this at 30 degrees. So okay people, this is clear. And you can see that once we have got this relation, this one which is giving us ultimately that DCM is root 3 by 2 L omega. It's the same as what we had got earlier. So obviously we get. Okay, so since I have a little less time left, I just want to go over the concept of instantaneous axis of rotation once first. So we have the concept of instantaneous axis of rotation for any rigid body moving with a combination of translation or linear momentum equal to mass into velocity of center of mass and rotation about the center of mass. So the angular momentum about the center of mass is ICM into m. So this linear momentum should be written by P. It is a combination of translation and rotation. So any such rigid body, even if it is not a free rigid body, it's constrained, then obviously you know the instantaneous axis is the fixed axis. But even when it's a free rigid body, it always has an instantaneous axis such that if this is the center of mass and it's traveling with an instantaneous velocity, BCM, and about the center of mass, let us say there is an angular velocity omega, then we can always find a point which is the instantaneous axis such that, so first of all, let's see the definition of instantaneous axis. What will be the definition of instantaneous axis? Okay. So the instantaneous axis of rotation, it will be a point about which, or it will be an axis about which the rigid body has a pure rotation with angular velocity omega at that instant. at the given instant. So what this means is that there should be some point about which, if we take the velocity of any general point in the rigid body, it should be omega cross r of that point with respect to the instantaneous axis. So it implies that the velocity of any arbitrary point P in the rigid body, part of the rigid body, Vp, has this relation with respect to the position of that point P with respect to the instantaneous axis. So that's the first thing. And also the angular momentum of the rigid body about that instantaneous axis will become the moment of inertia about that instantaneous axis into omega. This will be angular momentum about the instantaneous axis of rotation. And also the total kinetic energy of the rigid body will be half IO omega square, or half IO omega square will be the same thing as half mVcm square plus half ICM into omega square. Now you will see that if your statement about this thing is true, the velocity of any general point being omega cross r, then this statement becomes automatically true. Okay, because this is nothing but the parallel axis. So I'll come back to that. But first of all, let's understand in terms of definition what instantaneous axis means. It means that at a given instant, that body in combination of rotation and translation, it has an instantaneous axis. Instantaneous means that the axis may be changing with time, but at that instant, it has a particular axis, which is variable axis, such that us axis ke about it is in pure rotation. That means, first of all, the velocity of, so every point in the rigid body is in pure rotation about that axis. So it should have a circular motion type of velocity of omega cross r about that point. Secondly, the whole rigid body is in pure rotation about that point. So the instantaneous angular momentum should be I omega about that point. And thirdly, therefore, the kinetic energy should be half I omega square, where I is about that or about that axis, which also means this. Okay. So let us see the sort of understanding of this, why this happens. Okay. So let us say in a rigid body, again, the center of mass is right now here, let's say, and is moving with the velocity Vc. That's our center of mass. And about the center of mass, there's omega. So let us say I'm just arbitrarily now finding some point which I'm labeling as O, such that उस point के respect में अगर मैं center of mass को देखता हूँ, then the center of mass seems to be doing circular motion with the same omega about that point. Okay. So I'm not saying just now that okay, that point is the instantaneous axis. Maybe, may not be. Okay. I'm just saying that I can always find some point or some axis about which this property that we had written about IOR, that property is satisfied by the center of mass. That if we assume omega about this point and the position of the center of mass is RCN, so we appoint the axis at O, the axis to the instantaneous point O is such that VCN is equal to omega cross R of center of mass with respect to that. So if this thing is satisfied, for any given BCM and any omega about the center of mass, we can find such a point. This do we equation को satisfy कर रहा हो. Like for the rolling, it is nothing but the point of contact with the ground. If it is rolling with overspin, then that point actually goes inside the ground. If it is rolling with underspin, that point comes above the ground. Now think of any arbitrary point. Now think of any arbitrary point within the rigid body P. So इस point के respect में, I mean O के respect में उस point का position suppose ये R of P with respect to surface. Okay. So we can see that for any arbitrary point P in the rigid body, within the rigid body of course, what is happening is, in this diagram, you can see that we can write the position vector of that point as position vector of the center of mass with respect to O plus position vector of that point P with respect to center. This position vector RP with respect to O can be written as the sum of this position vector RCM with respect to O plus this position. This is the point P. Okay, so hence this statement. Now we know that since the rigid body has VCM, okay, and omega about CM. Okay. So in ground frame, the absolute velocity of that point is again the velocity of that point with respect to center of mass plus velocity of center of mass. So it is omega cross this plus VC. So that is the velocity of that point. Now bring in this relation. So we can write this quantity as omega cross. Now this will become what? R of P with respect to O minus R of center of mass with respect to. So we can write this as omega cross R of P with respect to O plus VCM minus of omega cross R of center of mass with respect to O. We can write this equation. And now compare it with how we have defined O. So the point O is defined such that VCM is equal to this. So these two terms have to cancel. So that's it. Now, the point O is defined in such a way that VCM is nothing but omega cross R of center of mass with respect. So that means the moment we define that point O in such a way, it implies that not only this relation is true for the center of mass, any general point has that relation. It is omega cross R of that point with respect. And if that is the case, then it's easy to prove that the angular momentum is I omega and the kinetic energy is half I omega about the instantaneous axis. So this is one of the what we call the rigid body theorems. The 4 rigid body theorems in all in rotational mechanics, important ones. And this is one of the rigid body theorems that if we can define a point such that, okay, so this theorem is basically like that, that if BCM is equal to omega cross of R or the center of mass with respect to some axis O, then it automatically implies that any other point also has a velocity given by omega cross R of E with respect to that point. So that point becomes the instantaneous axis of rotation. Okay, so just go through this once and make sure you're clear about this vector diagram. Okay, people, so hope this derivation is clear here. So it shows you that not only it shows you that such a point exists, which is the instantaneous axis of rotation, it also shows you that the angular velocity about the IOR is the same as the angular velocity about the center of mass. That omega is the common term, same for both. Now the next thing is you can see that angular momentum for the system about to, how we define this. So you take any particle of mass dm at the point P, and you can see that that particle has some general kind of velocity dp, whereas our instantaneous axis is, let's say, sitting over here right now. So about this, there is that omega. So the relationship between these is this. In fact, it should be perpendicular. So this velocity vector a little bit different. So I draw it now like this. So now the angular momentum of that particle about this will be r cross mv. So it will be r of that point P with respect to mv cross or rather dm. So this becomes r cross omega cross. So from definition of cross product, but triple product, you can see that this becomes dm r square into omega. We're just using a property of triple product that E cross B cross E will just become E square. So that is this. So angular momentum of the entire rigid body, so the integrated sum of the angular momentum of all the particles becomes dm omega just write it in this order. Omega is a constant for the integration. So as you take omega outside the integration, you see you're left with moment of inertia about the point. So the definition of moment of inertia about the axis. So you have that. So this implies that angular momentum about O is equal to, which by the way also proves your parallel axis. Also angular momentum about O can be written as RCM cross MBCM plus ICM into omega. Now you write this as IO omega and write this as omega cross r of center of mass, and you end up doing parallel axis. So I about some general point becomes ICN plus NP square, that kind of. Just give me a second, guys. I'll be share to board. This gives us the crucial parallel axis. ICN plus MD square kind of thing, where D is nothing but the position of center of mass with respect to that point. So nothing surprising there. And then similarly, you can define the kinetic energy. You can define kinetic energy in a very similar way. You can see the kinetic energy of that particle is half dm into dp square. So that is half dm into omega cross r of t with respect to that point. So kinetic energy, you integrate this thing. So you get that. Now this has a magnitude of this one, because they are perpendicular vectors. Omega is always perpendicular to r of p with respect to it, because this is defined as the position with respect to the axis. So it has to be perpendicular to the axis, and this is along the axis. So this is a radial vector, this is an axial vector, so they have to be perpendicular. So we end up integrating this thing, omega square r3 with respect to omega whole square. So that is again the same, half omega square into integration of r square dm with respect to that. So that is nothing but moment of inertia about. So this is your kinetic. So in context of how we apply this in problems, you can see that we are making use of all the three tools in various different type of problems. In the problem we just did, we made use of this thing. We made use of the fact that d of any point is omega cross of r with respect to that axis. Velocity of center of mass is omega cross r with respect to center of mass, and we made use of kinetic energy. We didn't really make use of angular momentum, but in other problems you can make use of angular momentum also. This is angular momentum of that particular axis. Here we made use of the kinetic energy. So these are the various ways in which we make use of instantaneous. Now there are some pitfalls which we will discuss with more questions. For example, we should generally speaking not apply torque is equal to I alpha about instantaneous axis. Because what is happening when you write the angular momentum as I omega like this, remember here I is an instantaneous quantity. So the moment I is instantaneous, when you differentiate this side, you get torque. Rate of change of angular momentum is torque. But this side is not necessarily a constant I into d omega by d. I could be changing with time because it's instantaneous. Okay. Only if you can be sure that okay, I is not changing with time. The axis is moving in such a way that the moment of inertia about that axis remains constant.
but that's very rare cases. So in general, we should avoid using torque equation about instantaneous access. You can write the angular momentum, you can write the kinetic energy in terms of the instantaneous access moment of inertia. And definitely you can use this kinematics kind of thing, that velocity of any point is omega cross r, including the center of mass. So those are the useful ways in which we make use of instantaneous access. Okay guys, so hope this session was useful for you. And I'm concluding the lecture here today. As always, keep sending your doubts and we'll discuss some of the doubts in the class and some of them I'll send you links. Okay. So wish you all the best, and that's it for today, people. Thanks for attending.